Now if you see this, the entire problem of this with lock is whenever a process is trying to set the lock, at the same time, if some other process is also trying to look at the lock, then there is a problem, isn't it? Let us say there is no TSL. Then the problem with the lock variable is when two processes look at the lock variable and preemption is there. So in order to solve this problem, one simple solution is maybe we could do like this. Assume that there is critical section. Now if you want only one process to be inside the critical section at any time, then what that process could do is, before entering into the critical section, it could disable the interrupts, right? So what is the interrupt, I'll tell you later. We shall discuss about interrupts in a very detailed way later, but now understand that the way in which one of the possibilities or main possibility or the main what I can say, the process which is used in order to preempt a process is, when the process is running, will send an interrupt, and because of that interrupt, operating system kernel will take control of the CPU. Then that operating system will decide whether to run this process or not. Now if we disable the interrupt, a process will never get preempted, right? So what we could do is, disable the interrupt, and then the process will enter this critical section and then enable the interrupt. If I simply write this one, which means if I give the control to the user process in such a way that when they want to enter the critical section, they could disable the interrupt, stopping every other process to compete for critical section, and once it is done with critical section, then it can come out and again let the other process get in. If it could do it, only one process could be inside this critical section, isn't it? So using this one, let's see this. First one is mutual exclusion is always guaranteed. The reason is, once you have disabled this interrupt, you will never get preempted. Therefore, there is no way more than one process can enter into the critical section, right? And second one is progress is definitely guaranteed. The reason is, if a process is not inside the critical section, or if a process doesn't need the critical section, how could it ever stop the other process from getting it? It will never stop the other process, right? Therefore, progress is guaranteed. And the third one is bounded waiting. This one is not guaranteed as of now, because it depends on the order. As long as you don't maintain a queue of processes which want to access the critical section, and as long as you don't let them go inside the critical section in a proper order, like in a queue, right, there will always be bounded waiting problem. So bounded waiting cannot be guaranteed, because that depends on the way in which you schedule the process. And the next one is architecture, right? So which means it is architecture dependent, which means it is not independent. Your architecture should be able to provide this control, interrupt control, to the user process. But the problem in this is, yes, these two are guaranteed, but this is not a popular method. The reason is, you can never give the control of interrupts to a user process. What happens because of that is, if you ever give the control of the interrupt to the user process, the chances are that the user process will never give the interrupt back, which means user process, once it disables the interrupt, then what happens is, there could be no other process, no one could take the control of it, so it can run forever, isn't it? Therefore, it is dangerous to give the interrupt control to the user process. So he might disable the interrupt, and then he might forget to enable it, forbidding every process, including the operating system kernel, to take care of get into the CPU, right? So this process is rarely used, even though it is mentioned in one of the books, but then it is rarely used. The disadvantage is, we cannot give interrupt control to the users. Got it?